Welcome back. This is a teaching video on section 5.6, projectiles launched at an angle. This is 3.6 in your textbook. We've seen that if you were to throw a ball straight out, it would have the velocity that it left your hand with forever until it hit the ground. It would accelerate towards the ground, but it would go straight out at a constant speed away from your hand. If you shoot a ball or throw a baseball or shoot a bullet or a cannon or something, or a spaceship at an angle, it's a little harder. You've got more math to do because you are not just dropping down from straight. You have to drop down from some kind of a curve trajectory that you're already on. So it's a little bit more difficult, and it takes a little bit of more time to figure it out, but it's still very doable. So the one thing I'd like you to remember right now is that the formula for finding out how far something has traveled based upon its time is it drops 5 meters times the square of the time. So for every second, say like after 1 second, how far does it fall? Well, 1 second is t, so t squared is 1, and 1 times 5 is 5. So after 1 second, it drops 5 meters. How far does it drop the second second? Okay, the second second, the first 2 seconds, is going to be 2 times 2, so 2 times 2 is 4, times 5 is 20. So it drops 5 meters the first second, it drops 20 total meters during the first 2 seconds. Okay, so during the second second, it must have traveled 15 meters. So it's 3 times faster the second second. It's 4 times faster the third second. It's 5 times faster the fifth second. So that is the first thing I'd like you to keep in mind, that it's getting faster based upon 5t squared, and the t is the time. So no matter what angle you shoot, the vertical distance is always going to be 5t squared. Okay, so it will drop 5 times the square of the time directly underneath it. It'll cover that vertical distance every second until it hits the ground. So depending on where you shoot it, like what angle you shoot it at, are you going to shoot a gun straight out from top of a hill? You're going to shoot it straight up into the sky and let it come back down somewhere, or throw it down into a valley or something like that. You're going to get still a parabolic curve, but it's going to drop at the same amount each second. It's going to drop 5, followed by 20, followed by etc. It's 5 times t squared. So the dashed straight lines show the ideal trajectory, like if you were throwing a ball up at a certain angle or out at a certain angle, as if there was no gravity. Where would that ball be every second if there was no gravity to pull on it? Okay, so that's why it's dropping straight across. This would be like straight across at the same amounts of time. This would be at an angle at the same amounts of time if there was no gravity to pull it down. Since there is gravity to pull it down, it's going to get the same arc. So after 1 second, it drops 5. After 2 seconds, it drops 20, etc. So the same amount of drop each second, no matter which direction you throw it at. So with no gravity, the projectile would go straight, okay? No gravity. But since there is gravity, in 1 second, 1 times 1 is 1, times 5 is 5. It drops 5 meters in the first second. It's going to drop 20 meters in the second second. Always. It's always going to drop the same amount. So that's why you're going to, that difference is always going to be growing, okay? As you get farther and farther and farther away from the cannon, the resultant is always going to be a beautiful arc. If you throw a ball or shoot a cannon, you're going to get a pretty arc. So with no gravity, the first second it's going to drop, or with gravity, the first second is going to drop 5, second 20, etc. Okay, so the third one would be 45, and then you end up with what we saw before. So your distance, we've seen this before, is the distance formula 1/2 at squared. And a, remember, is acceleration, and g is a special form of acceleration called gravity. It's the acceleration due to gravity. So 1/2 at squared was the distance of a marble rolling down a hill, but 1/2 gt squared is anything that has left your hand and the only thing acting on it is gravity. So height. Since you know what gravity is, since you know what the pull of gravity is, you could figure out how high something can go when you throw it. Okay, because there's a certain amount of pull that's pulling it back, and since that's always consistent, always constant, the height is based upon how fast it leaves your hand. It will depend on how high it goes. If you throw something real slow, it'll go a little bit of your hand. If you throw something very fast, it'll go very far away from your hand and then turn around and come back. So for the component factors of the cannonball's motion, horizontal component's always the same, and the vertical changes. So it's getting faster as it goes down, but if you throw something straight up, it gets slower as it goes straight up. And it's getting slower at the same rate that it's getting faster when it falls. So if you play catch with God and you throw a ball straight up in the air, it's going to get slower at the same rate as if you simply dropped a ball onto the ground. It's getting faster at that same rate that it's getting slower as it's acting out. So you can think of down as a positive acceleration, and you can think of up as a negative acceleration, but the acceleration is still the same, 9.81 meters per second square, faster down or slower up. So the velocity of a projectile is shown at various points along the path. Notice the vertical component changes while the horizontal doesn't. Okay, so the horizontal is going to go this distance, whatever that is. So wherever you see it, you're going to see the straight across is going to be the same, but the vertical is going to be different based upon gravity acting down. So let's see where it goes. Okay, you're going to see that these two are identical, but this is much, much slower because gravity has eaten away that velocity. You had a certain velocity when it started, but since gravity is acting down, it's eating away that velocity and making it slower, slower, slower. At the very top, what do you think the velocity is going to be? The very top, the velocity will be 0. So it stops and then turns around and speeds up on the way back. Okay, so this one isn't going to be nothing going up, so its velocity in the up direction is 0, but the velocity in the out direction is the same as it always has been. Okay, all the way through, that velocity will be equal. Now what you're going to see is you've got a downward acceleration. That acceleration or velocity, so your velocity was large when it started, small as it gets eaten up, but then once it turns away, it's going to start getting faster again at the same rate that it dropped coming up. So this amount here is equal to this amount here, and I would assume this amount here is going to be equal to this amount here. So when it leaves your hand at a certain velocity, let's say 5 meters per second, when you throw it up straight up in the air and it comes back down onto your hand, it comes at exactly the same speed that it left with. The gravity ate away the velocity and then gained the velocity in the other direction. So you're going to see that this was equal to this. Okay, the same amount. And that's if we don't consider air resistance. Resistance is going to slow it down. This is a beautiful, perfect mathematical arc, considering that it's not slamming into air molecules and slowing down. So the range, how far something can go away. So this is what you would want. If you want to shoot a three-pointer, or if you want to score a soccer goal, you need to know how far you can kick at whatever angle you choose to kick at. You want it to go right in. You don't want it to go above it, or you don't want it to fall short. So the angle at which the projectile is launched affects the distance of travel. And this may not be, might not occur to you naturally. You might actually have to kind of be shown this rather than it dawn on you. Okay, so look at these first two ranges. You can see that this range is very long, this range is very short. What's the difference? Okay, the difference was the angle at which you threw. This is a very close to 90-degree angle. This is like a 45-ish kind of middle angle or something close. And so the higher you go, that energy is being eaten away by going high. It doesn't go as far out. The lower you stay, the more ability you have to go far, but you can't go too low because then it won't go very far. Okay, so there's like a sweet spot that you're looking for of what angle do I kick a ball so it can go as far as it can go without like immediately stopping because I didn't kick it far enough and it went right into the ground. So there's kind of a trick, and I suppose that's part of what it means to be an athlete. You have to know these tricks with your body instinctively. So how far can something go? Projectiles that are launched at the same speed but different angles reach different heights, that's called its altitude, and they also go for different distances, or its horizontal range. All right, so here it is. You want to know how to make the basket. You want to know how to make the soccer goal. These are the angles. Now, the trick is having your body know exactly what angle to shoot at. But if you shoot at, you're going to get the farthest range. What do you see as the farthest range? Okay, if you shoot at 15, it goes pretty far based upon its arc, but it slams into the ground before you want it to. So you need to kick it higher so that it'll go a little farther. So at 30 degrees, you've got something farther. At 45 degrees, it's even farther still. At 60 degrees, you're going to see that it's the same as 30. And that has something to do with geometry, 30-60 triangles, 30-60-90 triangles. And 75 has the same range as 15. And it's exactly the same reason why 30 and 60 is 90, 75 and 15 are 90. So there's some geometry going on here, just like in pool or any other geometry game. So if you want to go the farthest you can go, you want to kick something at 45 degrees. Okay? Otherwise, you have to gauge where you are based upon where the basket is or where the goal is, and that is the angle that you kick at. And that only comes in an athlete by practice, because you simply have to say, I don't know how far I am. I don't know what angle I need. I simply have to do it over and over again to where my body learns at this distance I need this angle, and you don't even have to mathematically know what that angle is. It's just what your muscles tell you it has to be. So the same range is obtained for two different positions, angles that add up to 90, just like we saw. So the maximum range is attained when it's hit at nearly 45 degrees. That's how far you want it. You want to hit it at 45 degrees if you want it to go the farthest distance. So how fast can it go? Okay, we know how high it can go, we know how far it can go, and now how fast it can go. So without air resistance, a projectile will reach the maximum height in the same time it takes to fall from the from that height to the ground. Okay? So remember, it's like if I were dropping a ball, it's going to get faster until it hits the ground. Well, if I hit that ball, if I make that ball go straight up, it's going to get slower at that same amount. So whatever the height was that I dropped it at, it's going to, at that speed, it's going to reach a maximum above my head, but get slower up to that point. And so the speed is going to be the same. If you throw a ball and it's at 10 meters per second from your hand, it will land in your hand at 10 meters per second. Okay? So as it's higher, it goes all the way up to its maximum arc at 0 meters per second straight up. But then anywhere along that up-down range is going to be less than what you started, but greater than 0. And the The elevation will tell you what the speed of the ball is horizontally. Vertically. Horizontally, it's always going to be the same. Whatever speed you threw something straight, it's going to maintain that velocity until it hits the ground. So I hope this makes sense. If it's 50 meters per second here and it's being eaten away because of gravity, and it's only 30 meters per second here, and then 10 here, eventually it goes to 0. So this is 0 straight up. Now we're only talking about up speed, okay? Well, it's 0 up speed. Well, as soon as it gets to the same height that it was before, whatever elevation that is or altitude, it's going to have the same magnitude of speed. It's just in a different direction. Instead of an upward slowing down speed, I've got a downward getting faster speed, but the speeds are the same. So 30 and 30 is based on its altitude or its elevation. 50 and 50 is based on its altitude or elevation. So the ball is going to hit your hand at exactly the same speed that it left your hand at. Okay. Problem with air is air slows you down. Okay. It slows you down in a couple different ways. It slows you down up and it slows you down out. So you're not going to have the gorgeous parabolic arc that you would draw in math class, because it's not just the up-down ones that's slowing down, it's also the sideways ones that are slowing down. So your actual path is a little bit wonkier than your ideal path. And the math is a lot awful, so I ignore it totally. I hope you don't mind. So think about this. A projectile launched into an angle into the air, neglecting air resistance. What is its vertical acceleration? Not a trick question. What's the acceleration of gravity? That's its vertical acceleration. The acceleration of gravity is 9.81 at the Earth's surface. And so going up, it's 9.81 being eaten away. Falling down, it's 9.81 getting faster. Okay. What about its horizontal acceleration? Is your ball getting faster as it goes farther away from you? Not at all. Your ball is going the same speed. It goes at constant speed horizontally. The only thing that's making it speed up or slow down is the acceleration of gravity acting down. That's why. So its vertical acceleration is 9.81. Its horizontal acceleration is 0 because there's nothing making it go faster. Once it left your hand, there's no force that's pushing it farther or slowing it down, and so it's going at a constant rate. New question. At what point in the path does a projectile have its minimum speed? Okay. Well, it depends on what you're talking about. If it's outward speed, it's going to be the same. If you throw something straight out from you, it's always going to have that same speed in the outward direction. But what about you throw something up? Okay, it left your hand at a certain speed, it's slowing down, slowing down, slowing down. What happens when it gets to the top of the arc? It's no longer going up because it has no more horizontal velocity. Your velocity has been eaten away all the way to 0, and then it speeds back up as it comes back down. So you have a 0 at the top of the arc. When you have whatever this arc is, this upward speed is 0. Even if this were 1,000,000, eventually it's going to raise up, and whatever comes up must come down. So describe how far below an imaginary straight line a projectile falls. This was what I asked you to remember that first slide. How far does it fall? This is important. It falls 5 meters times the square of the time that it falls. So that's how far it falls beneath the imaginary straight line path, as if there was no gravity. Okay, I hope this helps you.